because these are all related types, related concepts. A composite type is used to create recursive structures. Just because you've got a composite type doesn't mean you have a recursive structure. So, in fact, they're all related. Okay? So I actually do this in Comp 110. And so you guys who've done your first programming course, your instructor never did recursion? I assume. How many of you had professors who did recursion in your class? About 4 people? And what about those 5? Those of you whose professors didn't do recursion, you probably had textbooks. Did those textbooks have recursion? They did? Okay. When I first taught Comp 110, I asked the professor before me, what should I do? And in particular, should I do recursion? And they said, nah, it's too difficult for these guys. So, of course, I had to try it. And because I loved recursion. And at the end of the class, I asked people, what was your favorite topic, the students? And I also saw the scores on the final exam. And nobody got the recursion question wrong. Okay, they all got it right. And even when I asked the survey, they said their favorite subject was recursion. Okay, so I think it's easier than it's thought to be. And, we've been talking about recursion, recursive methods, method calls. So all this is going to be pretty simple. But you'll at least learn some general principles that will apply to doing more fancy recursion. Now that we have the composite design pattern, we can do recursive methods, and we look into those. And before I take that big step, let's take some smaller steps. Okay. So if I was to go up, look up the dictionary for the word what recursion means in English, what would it say?
If you Google it, it will offer you. It will say, "Did you mean recursion?"
Really?
Yes.
It typed the word recursion into Google. It says, "Did you mean recursion?"
You know what? This has been my joke. You'll see that joke come here. I didn't know Google also had it. Yeah. Well. Nobody will think they stole from me. But anyway, if you look up the Webster at Oxford dictionary, okay, which is the way I looked at it when I first taught Comp 110, this is much before Google came around. What would it say?
If you go recursion, it says C recursion.
This is my joke. Okay. But what would it? Does it say that, by the way? Not the recursion. Webster and Oxford? No, they don't do that.
Oh, no. I've seen some dictionaries.
Yeah. So if I go and they'll say return, and that kind of confuses me because I'm so immersed in computer science language. So what do you think it says return? I mean, really, that's a real question.
Return to the start of what you were at.
Okay. Or reoccur. I'm thinking recursion probably comes from reoccur. It's probably an abbreviated form. A true English major would tell me if I'm right or wrong, what the origin of the word is. And so when something reoccurs, it's recursion. But they actually are pretty good. The definition is pretty consistent with how we computer scientists view things. So the procedure of repeating itself indefinitely or until condition met. Okay? And when we were doing the grammar rules, we were doing things recursively. Okay? In fact, your parser implementation is called recursive descent. And that is also recursive. And I try to find, and you hear this all the time. So and I think this is true. I looked this up a long time ago. That adequate, it'll say satisfactory. And if you look up satisfactory, what do you think it'll say? Okay. So we find this all the time, and that makes sense. You might know what the word adequate means from context, and then you want to look up satisfactory. You'll know what that means. Or you might have learned satisfactory in some context, and so it's not too bad. And of course, this is my joke. Okay, so this is how I would have defined recursion, and actually they should put in Webster and Oxford this. Mathematics. So a recurring series. They talk about that. It's expression giving successive terms of a series. And the basic idea is that we have a method calling itself, okay, and it's on a smaller problem generally. And the reason why Comp 110 instructors don't deal with recursion is because they say you've got loops, and recursion is another way to do the same thing. That's an advanced sort of thing, And let's just learn loops. Okay? And that's what people do when they teach programming in what's called imperative languages. Okay? And Java, JavaScript, whether it's an object-oriented language or it's non-object-oriented language, many of these languages are imperative. And they're also called procedural languages. And the opposite of procedural language, can you imagine what the word would be? Functional. Okay? And functional languages tend to go and not teach loops. In fact, they don't even have loops. And they would just go and teach recursion. Okay? And a lot of people think that people who learn functional languages become better programmers. So it seems that when you have recursion in a language, why not teach it? And the classic example, everybody uses it, and I'm going to use it too. Okay? For recursion is the factorial. Okay? And the factorial is of a number n is the product of the first n numbers, starting from 1. Okay? That's what I've done in English. Maybe it's ambiguous, but you'll understand it. And here's what I did in sort of symbols, but who knows what this ... means, and I'm just hoping you know what that means. Okay? And I could write a factorial function using loops. Okay? And in fact, I think when you guys learn loops, this is probably one of the first examples you might have seen. Okay? Every book's got it. Okay? And there's many ways to do loops, and a loop here, and I've just used a while loop. And here's my main program, whose output I'm seeing here. So you go and say, I want the factorial of this number. It says factorial is this. You say, I want the factorial of this number. It says factorial is this. And you say, I'm tired of factorials, -1, and it terminates. Okay? And here's my loop that's doing this. So before I kind of go into, and I know a lot of you just know exactly what the recursive alternative to this is. And before I go to that, let me just sort of motivate it by saying, I don't want to go and rely on this ambiguous specification. Okay? I don't know what this ... really means. I want to define this. Okay? And I don't want to rely on the English language and say, people understand when I say it's a product of the first n numbers. What does that really mean? Okay? So let's just be precise about what we really mean by factorial before we try to figure out how to solve it. And if we are not, then we really can't prove that what we've done here is what we want. If we can't even specify what we want, then we can't prove it, and well, that's life. Okay? But at least in some cases, especially this mathematical example, we should be able to do better than just run a bunch of test data and say, yeah, it's right. Okay? So if I was to go and tell you define factorial mathematically, rigorously, what would you do? Okay, you would say, well, factorial of 0 is factorial of 1. Okay. Factorial of, but we see a pattern here, right? And factorial of 2 is, right? And so the factorial of some n is this. Okay? No relying on ... All I can do is say this. Can I just say this only and say nothing else?
No, we need a case.
I need to say what, a base case, which doesn't have recursion. And now if I was to go and write a Java program, so here's my definition. If n is 0, then factorial of n is 1. And if n is greater than 0, factorial of n is n star factorial n. Okay? That's my definition. Okay? And from this definition, I can go and write a little function. Okay? And that function would just essentially put in code what I just said in the definition. If n is 0, return 1. If n is greater than 0, return n star factorial. Is this function right? Hint, it's not. If you write this, will it even compile?
Yeah.
What's wrong with this?
It needs to always return value, and if it's less than 0, it will return value.
Okay, so we're using ints. We don't have in Java a type that takes the natural numbers, okay? Natural numbers, so positive numbers and zeros. So firstly, we're having multiple returns here. Okay, we're having an early return. We don't have a return at the end. We return early. You've seen a lot of this stuff. And we are not returning in all cases. Okay, what about n less than 0? Okay, now, if I had done exceptions at this point, if I could assume exceptions done at this point, we could throw an exception. Okay? But we don't know exceptions at this point. I will cover exceptions, I think. Okay. So what we're going to do is just cheat and say, well, if it's less than 0, we're just going to keep Java happy. And we are going to say factorial of minus n. Okay? So you just convert that into a positive number and return something. And it's not total nonsense value you're returning. It's something that the user will be entirely surprised by. Okay? So we had to go in, because our argument is an int rather than positive and 0 numbers, the 0, we had to go and do this kind of cheating. Okay? That's recursion. Okay? That's the classic example in the case of recursion. Okay, so we have a base case. Okay, and what exactly do we mean by base case? So ultimately, we want this step to be taken. Okay, anybody else? I would have, given your previous answer, I would have said it's a non-recursive state. Okay, that's what it really is. Okay, it's the part where you don't recurse, because if you only recursed, then you'd never end. So it's a terminating case. Okay?
Typically, it's at the edge of your possibility to value, so it's a natural number.
So it's at the edge.
Yes.
Okay. So it's okay. Put it in the middle. Do you mean physically in the middle of the code, or so we don't quite know what edge is, but when we recurse, we have a recursive step, and I'm also calling it. I'm calling this a base case, and I'm also calling it a terminating case. I'm calling this a recursive step, and I'm also calling it a reduction step. What do you think I mean by the reduction step?
Because it reduces it to a previous problem?
To a smaller problem. Okay, the problem is going to arise later, actually. We're going to call it later. But we've got this large problem to solve, and we are solving a smaller example. And then the edge case would be the smallest possible. Okay? And that's what you might mean formally by edge. Okay? What does smaller mean? We'll see. It depends on context. But in the case of numbers, it typically means going to a smaller number. Okay? So should have base cases, should recurse on smaller problems. Recursive calls should all converge to base case, which is kind of what we were saying. Okay? So in general, your thing would be if base case 1, else if base case 2. You might have more than one base case that you converge to. And then you might have more than one recursive cases also. So you just must make sure that your recursive steps finally end up in some base case. Okay? Okay, yeah.
It seems very functional. I mean, it doesn't seem very object-oriented.
I have a method calling another method.
I don't have a problem.
We'll see. Okay? All I've done is write a method that calls itself. There's no reason why that method can't be part of an object. Okay? And there's no reason why those objects can't cooperate with each other. Okay? In this case, it's static, but we'll see recursive examples where it's not static. Okay? It just so happens that there's no state in this function. Okay? And that's why, and when you say that, that follows what happens in teaching, that people tend to focus on recursion in functional language Yes, and in functional languages, your functions do not manipulate any state. So yes, you're right in that sense. Okay? But in general, recursion could occur in other contexts. Okay? So let's go and figure out first, we could have done it with loops. We're doing it with recursion. What are some pros and cons? So what do you guys think? I've got this solution, I've got this solution. Which do you like better? Or you have, which would you write? If I was to ask you to write a solution, which would you write? Or, okay, let me first ask that question. How many of you would write the loop? How many of you would write the recursion? The others won't write. Okay, if I was to write, okay, how many of you are convinced that this particular answer is correct? This one, recursive one.
Correct.
By definition. I've already got a definition. I've got a formal definition. How many of you are convinced that this is correct? It doesn't have a off by one problem. Should it be greater than 0? Should it be greater than equal to 0? Are you all convinced at this point that it should not be greater than equal to 0? You're not. Okay, you try it out, okay, and you'll put either greater or greater than equal to 0. Okay? Whereas here, you don't have this off by one problem. Okay? Yeah, Murray?
So you're saying it's better because it more closely mirrors the language of mathematics?
I'm saying it more closely mirrors the definition of the problem, which I happen to use mathematics to define it. From my specification, I went into the solution. Yeah, I put this little. Sorry?
What is this off by one problem?
Do we know n is greater than or equal to 0 or what?
Okay, this is when you write a loop, you never know whether it should be greater than, equal to, greater than. You have to really write. This is where people who like assertions love to go and show assertions being used in loops, because you can, through preconditions and postconditions, really derive whether it should be greater than, equal to 0 or greater than 0. Okay? And you have off by one when you miss out. Either one case, or you either include something you shouldn't have included, or you exclude something that you should have not excluded. Okay? So it's much harder to reason in general about loops than this. You have all kinds of proofs given for loops. You never have proofs given for recursive methods, because what proof will you give? It follows directly from the definition. Okay? So you have things called loop invariants, loop preconditions, loop postconditions, and you don't talk of the same thing in recursive. Okay? So when in doubt, I personally write recursive, and there are certain problems for which the non-recursive solution is so painful that those are given as entire projects and courses. Okay? Go and do this problem non-recursively, and it's a real thing. So the implementation follows from the definition that we had, whereas that's not the case. Okay. Now let's try to understand whether it's good or bad. Let's try to understand how it really works. Yeah.
I think kind of recursion is you have three things and it just spirals down between them as opposed to jumping back to two.
What do you mean?
Alright, so if we're going to look at it as states, then you have three states, all of which point to the other one, and it spirals down until it gets to a certain point. So you have three methods that call each other in a defined order, as opposed to one method which just calls itself.
Yeah, so you can have mutually recursive methods.
Okay.
In fact, I gave the example of adequate and satisfactory in that fashion only. The adequate called satisfactory, and that called. So you can have mutually recursive methods. Okay. Now let's try to go and figure out what's really happening. Whether you like recursion or not, let's try to understand it at least. Okay. So I have my main method called factorial with the number 2, and my stack is this. And how long will my stack get before I stop unwinding the stack? So I'm going to grow my stack and then go in. Ideally, in any method, in any program, your stack grows and then finally should shrink. Otherwise, you just keep growing. Okay. So how many calls will I have before I start popping from the stack? Factorial 2 will call factorial 1. Will factorial 1 call another factorial? So I'll have factorial 2 called factorial 1 called factorial 0, and then we'll start returning. Okay? And the value n will be the same in all methods or different? Okay? So this is my local variable. Okay, this is where you really see that these variables are local and they're not shared between all methods. Okay? So I start with factorial 2 and my n is 2. Okay? So factorial 2, we don't know what its return value is, but we know factorial 2 calls factorial 1. Okay? And that then calls factorial 0. And we don't know what factorial 0's return value is immediately. And then we go to this stage. Okay? So we know what that value is. And here's a call stack, just as we said. Main calls factorial, calls factorial, calls factorial. Okay? At this point, we are ready to pop the stack. Okay? So n is now 0. So we're going to return 1. So I can fill my table and go and say factorial 0 is 1. Now that I filled that table, I can go and look at the n star factorial n minus 1 and say my factorial 1 is 1. Now that I've got that return value, I can go and fill up the factorial 2 value and say it's 2 star 1. Okay? So this is the order in which, this is exactly what's happening in the language. Okay? The calls are made, the stack is put, the stack contains n, the stack contains also a slot with a question mark saying who knows what my return value is, and that return value gets.
It seems then that a loop, while maybe with the year problem solving will be slightly more efficient in this case, because it doesn't have to step back in the way.
So the loop would be slightly more efficient. Actually, it would be, in the good old days when computers were slow, a method call is many, many instructions. Okay? And you have to go and push this, you've got to allocate memory from the stack, you've got to deallocate from the stack. So there were the purists, the functional programmers, and there were the hard-nosed people who got things working fast. And their argument always was that loops are much more efficient. Okay? Because you don't have to go and do this pushing, popping of stack, you don't use up memory. And in those days, a procedure called was called. Okay? And it's very interesting, as computers have got fast, what's changed? Okay? Well, the graphics guys are just so happy because they can render things fast. Okay? The researchers aren't so happy because the need for their algorithms is less now. Okay? And because you want problems in life if you're a researcher. It's kind of ironical. Okay? And the software engineers are happy because they can bloat their code. They can make, and it's interesting because I told you I dealt with Xerox computers, and those, they had the first Windows system that I pretty much see on my computer today. And my computer today is God knows how many times faster than those computers. But I don't see a response difference. Okay? And that's really because we have layers and layers and layers and layers of software now. Okay? And now we have security checks going on in addition to. So part of what you get from fast computers is this modularity. Okay? And I've seen messages from people saying, we want to make our programs fast, so we just remove object editor. And sure enough, object editor does slow things down. That's because it's just layers and layers and layers. Anytime you get an error, you just see a long trace. Okay? And you just know how many method calls happen before anything really gets done. Okay? So, and part of the reason in case of object editor and Eclipse is that Java is this a language that loads modules dynamically. So as you need a module, it says, let me go and read this file and get this. Languages like C++, they just said, okay, I know your whole program, let me just load it all up at one time, so I don't have to go to the disk and get things again and again. So loading time is really high in Eclipse, in object editor, and when things are running, things are running. Okay? But yes, this is the classic argument against recursion. Okay? But today, with the fast computers, I'd rather have a correct answer. The human cost is much more, and the computer costs, that's why we need to keep Intel in business, and so we want fast computers. Okay. Okay. Other things. Okay. So what if I went and just wrote this line? What's going to happen? Factorial 2, factorial 1, factorial 0, Negative infinity, if we had negative infinity. Okay? And that's when you see how quickly your computer can use up its memory. Okay? So you'll get your stack overflow error. Okay? That's another thing that you won't get with loops. Okay. Okay, and so the problem is there's no base case. Okay, that's the problem. How about this? Factorial of n is factorial of n plus 1 divided by n, no?
Technically a true statement.
Technically the true statement, but you don't like it. What's going to happen? Divide by 0?
No, I don't think we're ever going to actually get that vision you have.
So what's going to happen? Factorial 2. So we call factorial 3 by 3. Wouldn't it be nice if we had the 0 problem? We're not even going to 0. So what's wrong here? I've got my base case, I've got my recursive step. What's gone wrong? You're going away from it. You haven't reduced the problem. Okay?
You're not recognizing your base case.
You're not converging to it. Okay? We are recursing on a bigger problem. Okay? So recurse on a smaller problem. Please don't recurse on a bigger problem. Okay, so we've been very functional right now, and if you really like this, you question why you ever learned Java, why you ever learned objects, why you ever learned patterns, so this may be the wrong thing to be doing at the end of a class where you've been creating big objects. So let's go and see whether if you move away from functions, recursion is still useful. Okay, before we do that, sorry, I lost track of where I was. I haven't taught 110 for years and years, so I don't know what comes next. Okay, let's stay with functional methods. Okay? We'll go to that later. And let's try to go and do another problem. Now, factorial is not the only problem that we do with recursion. And let me try to do this one. And this is more complicated because we've got 2 parameters. And what I'm really doing is saying, please multiply base exponent number of times. Okay? And I can say power of 0, exponent is 0. 1 exponent is 1. 2 is 2 multiplied by 2 multiplied by 2 exponent times. 3 is, so I'm trying to derive a little functional recursive step. But I don't seem to be succeeding very well, do I? There's no real pattern here. So maybe this is a problem we don't do with recursion? Right?
You should be considering your exponent of your base.
So we had 2 parameters. We could have reduced one, the other, or both. And I took the wrong choice, maybe. So let's try the other way. Power base 0 is, power base 1 is base star 1, which is equal to power base 2 is power base power. And so what's my general formula? Power base exponent is equal to
Base times power of base exponent minus 1.
okay, base times power base exponent minus 1. Okay, so recursion is not that trivial, okay, that's my answer. Okay. Okay, now let's go and address the issue I was talking about. Let's get away from functions. So, the classic non-functional program that people write is the Hello World program. So we're going to try to see whether we can do that problem recursively, maybe. Okay? So we're going to have a method that will greet, if it takes an argument n, it will greet n times. Okay, so greet 0 will do nothing. Greet 1 will print hello. Greet 2 will print hello twice, and so forth. Do you guys see how you could do this recursively? You could write a little loop that goes for I equals 1 to n. Okay. Greet. But can we do this recursively somehow? So no functions.
The greet function will be print hello and then greet minus 1.
Print hello and greet n minus 1. Okay. So the pattern is that when it's greet 0, we do nothing. When it's greet 1, we do nothing, followed by print hello. We greet once and do print hello. We greet n minus 1 and print hello. Procedures, recursion. No functional language. I mean, functional language will never do something like this. Okay? So and again, my definition is, it's not mathematical, okay, but it's recursive, and it says greet n, do nothing if n is less than or equal to 0, otherwise greet n minus 1 and do print hello. Okay, if n is greater than 0. And my procedure would be, if n is greater than 0, greet n minus 1, followed by print and then hello. Do we have a base case here? So base case is terminating case. So if it's not greater than 0, we do nothing. That's your base case. It's terminating. Right? Okay, so we've done functional recursion, we've done procedural recursion. Let's do list-based recursion. Okay, this is what functional languages are excellent at doing. They have beautiful data structural lists, and you can do really fun, enjoyable recursive methods on this. Okay, Java has lists, but it becomes cumbersome to use them when you do recursive methods. Okay? In your assignment 11, did you guys do some kind of list-based recursion where you're going through elements of the list recursively? The answer is yes. I kind of told you what to do. Your token list, you were going through the tokens one by one, right? And you were calling parse command, was calling parse repeat command, which is calling parse command. So there was recursive methods there. And weren't you going through the list? That you started with a list of all tokens. As your index incremented, you essentially said, this part of the list is consumed. I'll never look at it again. Now I'll process on the remainder of the list. And as you called your parsing methods, you were going towards what is the base case of a list? A base case of a number is a smaller number. The base case is the smallest number. The reduction step is a smaller number. In the case of a list, the reduction step would be index is just one way to go and represent, right? So it would be a list that is, where I said a smaller number, you would see a smaller list. Now, I don't know how to quite represent a smaller list in Java, so we said the index. We passed the index in the method saying, this is the portion that you really have to look at. So the portion I'm looking at is smaller. Whereas in a functional language, you would just say, get the head out, and the tail is what is the rest left. So you would always go, there was a head operation and tail operation, and you would pass to the recursive method the tail of the current list. You would process the head and do the tail. Okay? And that's like a stream almost. That whenever you consume things from a stream, you have the remaining stream left. Okay? So I really racked my brain as to how to go and show you the joys of list-based recursion. And I'm using the input stream, okay, which is like your token stream. We don't have an index, but internally Java is keeping an index. And I'm saying my multiply list, if my remaining input is -1, I'm going to have an input that's terminated by -1. Okay? If my remaining input is -1, the multiply list will give you 1. Okay? If the remaining input is 2 minus 1, it will give you 2. Okay? If it's 2, 6 minus 1, it will give you 2 multiplied by 6. So basically, what I'm doing is I'm multiplying all the elements in the list. And -1 is just a terminating element in the list because I don't have a better way of creating a list. Okay? So in general, with a list of n elements, a list of A1 to AN, I want multiply list to be A1 multiplied by A2 multiplied, so ... to AN. Okay? How would I represent that recursively? Supposing I have a method that says consume the element in the list at the head of the list. Okay? Read next token. Supposing I have a method called read next token, which just consumes and which gives you the next integer. It removes that element from the list and gives you the number that the element is. So I want to write multiply list. I've got read next token. How might I go and read? How might I go and write my recursive method?
Are we starting at the top of your thing or at the bottom?
So I'm starting with some list. It could be 2, 6, minus 1. So I've got read next token, which will give me an int value. If that read next token returns minus 1, what should multiply list return? 1. Right? If that read next token returns 2, what should it return? 2 multiplied by? Read next token is what 2 was. So we don't know what's coming after that. My read next token is 2. It may be followed by minus 1. It may be followed by 6.
If we multiply by read next token again.
So read next token is what I get.
Read next token of
My multiply list takes no arguments. If read next token returns minus 1, my multiply list returns 1. Okay? So read next value multiplied by, if it's greater than 0, And so basically, I would do it this way. I would go in, say, next value is console.readInt. If next value is less than 0, return 1. Otherwise, next val multiplied by multiply list. Okay? This is sort of the classic list-based recursion that you see a lot of in functional languages. Okay? Questions?
Is it somewhat similar to command list we have to implement in our channel?
No. It's similar to the token list. Okay? Command list is like your composite pattern.
Oh, yeah.
Okay? But your command list, all you're doing is going through a loop and executing one. And you could do that recursively if you wanted to. Okay? But this is more like you already got a recursive method there, and that is your token, your parse token. And that's always taking an index. And it's taking larger and larger indices to represent the fact that more and more elements have been consumed, and fewer elements have to be consumed later. So it's pretty much that's what you're doing there. You may not be aware of it. And had I not given you that index thing, it might have been a little hard for you to come up with that argument. Okay? But if you're really well versed with list recursion, it would have been a little easier for you to do that. Okay?
I'm having trouble getting your larger analogies and things to apply to the alternating harmonic series.
There are a lot of problems for which recursion requires some thought. And that's something you should probably look at offline. Okay? Okay, so tracing multiply list. Let's go and see if we understand this properly. So we have multiply list, and we have 230 minus 1. And return value, we don't know what it should be. But it's going to go and call multiply list. It's going to read the next value 2 and call multiply list with 30 minus 1. That's what the remaining input is. Who knows what the return value is going to be? That's going to consume 30 and call multiply list with minus 1. It's going to say 1. Then it's going to say 30 multiplied by 1. Then it's going to say 2 multiplied by 1. Okay? This we go and see recursion at work. Okay? So we have seen recursive functions, recursive procedures, number-based recursion, and list-based recursion. Okay? And recursion is easy to describe in some of these contexts. Maybe the factorial case was easy. Maybe all the other cases were a little hard. And in general, recursion is not so easy. In fact, your whole next course is going to be about recursion and the ways to use recursion. And so, if you say that, look, some things I don't quite know how to do recursively,